Alright guys, let's take a look so that you can see the screen. Or you can just blip into it. Homework 2, the binary hex worksheet. It didn't cover ASCII, so we'll probably have another assignment and another brief refresher on that. But I just wanted to make sure that we were all good on this one.
And due today?
No, not due to date. If it says it is, that's a mistake.
Yeah, it was next week, okay.
Yeah, next week. Okay. Good deal. All right, when you do your conversions, do you have to go to the trouble of setting up a table and stuff like that? No, not really, but you need to memorize, you know, the powers of 2 that make up a binary number. So if we were going to convert 11010, 11010, we can ignore all the zeros. And you'd just be adding 16 plus 8 plus 2. And that's it. Add those up and hopefully you get 26. See if I got it wrong. I don't think I got it right.
You did.
And if, you know, there were more digits, you just carry it out. 32, 64. And if you like thinking of it in terms of powers, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. But it's easier just to go 1, 2, 4, 8, 16. The place where the powers of 2 actually help a little bit, or not powers of 2, but where the powers start to help a little bit is when you're doing the same thing for hexadecimal. Because hexadecimal, you've got 16 to the power of 0, 16 to 1, 16 to 2, 16 to 3. And the powers business, there's no magic to that. You just say, okay, 1. You always have a 1's column. And then whatever your base is, 16, and then multiply that by 16, and then that by 16, and that by 16, and so on. And so if you were going to do octal, which is base 8, which we're not, then you put an 8 there, and this would be 8 times 8, and that would be 8 times 8, and so on. Okay, so the first one was just convert this binary to decimal the same way you did that one. And then, you know, a couple more problems. And then so on the second page, here's our binary to hex worksheet, which just shows, you know, the binary values 0 through F, their decimal values 0 through 15, and the binary equivalents. Why would you need to know that? If you were trying to convert, you know, D39X to binary, to decimal, you'd need to know that a D was a 13. You know, 9 and 9 and 8 and 8 and 7 and 7, those are easy, but you just have to remember that A 10, B is 11, C is 12, all the way out to F being 15. Now, this one doesn't involve hex. It doesn't involve that kind of conversion because this one is just doing hex to binary, which is just a lookup process. Right? What's a D? I looked it up. It's a 1101. What's an E? It's a 1110. What's an A? It's a 1010. And if you had to, you could make this chart yourself. You know, it'd take you, 2 minutes to write that stuff down. It takes you longer to type it in than to just write it down on a piece of paper. You just write the numbers 0 through 15, the hex values, 0 through F, and then the weird ones, do the binary odometer from 000 to 1111. But on any quiz I give you, any exam I give you, I would give you that chart. And so just doing the same thing, you'd fill in the yellow blanks. All right, so converting base 16, there's a little bit of notes in here as well. This isn't strictly part of the assignment, but it gives a little explanation of base 16. And then our powers of. 1, 16, 256, and 496. Why is that important? If we were going to convert a number like 12AF to decimal, well, there's 1, there's 2, there's A, there's F, and so you just multiply them by their equivalent power. 1 times 4, well, that's dumb. I love it when I get the example wrong. I think I got the right answer, but I got the example wrong. I mean, I made a typo there. All right, 1 times 496, 2 times 256. What is A? A is 10. So 10 times 16. And what is F? F is 15. So 15 times 1. Add them all up. You know what? If I say show your work, if you got your work right, I'm not going to care whether you got the result right or not. I mean, yeah, if it's ridiculous looking, you just write down, you know, some random number. But if it's off by a little bit, this is the part that I want you to know, because this is the important part, right? The rest of it is just using a calculator. So, convert, doing the same thing there. Looks like I only threw an actual one actual problem like that. I'm going to save and re-upload this because I did have that error there. If I was awesome, I'd give y'all more problems like that, but yeah, that's enough. Let's update that. Keep forgetting to bring a long sleeve shirt or a jacket for this room.
Okay, this has been loaded for about.
Pardon me?
It's been loaded for about more than 10 minutes.
Okay. I'm going to do the world's worst thing you can do to a stuck computer. Try it once more. Are y'all able to log in?
Mine did the same thing.
Yeah. Oh, by the way, who was trying to use the trial version of it? It looked like the trial version was going to expire really soon, like today, which is kind of dumb, right? That wasn't much of a trial. I thought we had got a whole month, but you were getting an error message when you tried to access the trial.
Well, I had logged in for 2 days.
Yeah.
And kind of realized I didn't find my key that I purchased the bill.
Oh, okay. 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 So anyways, the fact that it expires in 2 days is ridiculous, but sorry about that. I don't know if there's anything I can do to fix that. Yeah. Yeah, so you're good. Okay.
So I bought the book and I put in the access code, but for some reason when I go to the MindTap website, it's asking me for a username and a password, but I never made one. I just used my email.
Right, okay. Did you access MindTap through D2L or did you go to the
I was
MindTap
using
website?
DQL.
You did?
Mhm.
Well, good
But
question.
when I go to the Cengage website, I can sign in no problem.
And then can you go back to the MindTap link and it magically works?
You can have to either one or the other. For the day, they might either be locked to DCL, or they locked to the website.
Put this on lecture. If you're having trouble getting in the video, if you're having trouble getting into MindTap, if you follow this link and it says code has already been used, then come down here to the bottom one that says alternate link, and you should be able to get into it that way. All right, I do apologize for that problem. I had to do that last semester too, and I hadn't figured out that it was because people were purchasing it not through the D2L link. Now I know, sat a bit wiser. let's press to boldly go. Were we not done with chapter 1? Yeah, we were. Okay, good. Were we not into chapter 2? Guess not. Okay.
Alternative?
So do read chapter 1, take the chapter 1 exam early and often. I don't assign due dates to those, don't let that trick you. As a reminder that once you go into MindTap, you have a couple of views you can see. Like I said, I have complaints about MindTap. If you go into MindTap, la-di-da-di-da-di-da-di-da, it may come up with this page that says no activities due. Instead, I'm getting a teacher's view of it. You might check to see if there's something called the original dashboard versus the new dashboard. Yeah, this is the one. There are no activities with due dates to this. Kind of play with going through those. The original dashboard gives you the ability to view it by calendar and then by list. You'll want to view it by list. That gets you all of your resources right there, which I think ought to be the default to begin with. So chapter 1, you can read it, code, etc. I want to see what the coding exercises were for this. I decided not to assign the coding exercises because MindTap was extraordinarily picky about how you typed it in, and if you had a single, anything wrong with it, it wouldn't give you credit for it. But if we can look at it by hand, we can probably get that to work. We may just do the coding exercises in Python if the chapter 1 coding exercises look worthwhile at all. I will go and unhide the coding exercises that are hidden. I think I only did that for the first few chapters. Really? Have I hidden it to the point where I can't get it back? Alright, this is a waste of time. Let's... Phooey. I should just start the recording over. This is pathetic. Alright, we're going to go straight to the PowerPoint. I'll figure that out. So, elements of high quality programs. We've already seen a flowchart that is an impossible flowchart to implement in modern day languages. Many modern day languages. And what do I mean by that? It takes advantage of a construct called goto, which was invented back in the very, very, very earliest days in the 40s of creating computer programs. But here's the way it worked conceptually. This is not going to be a real program. Suppose we wanted to make a little loop that would count from 1 to 10. Set x equal to 1. print x. X equals x plus 1. If x is greater than 10, go to 150, else go to 100. Something like that. And then 150 was a print done. Right, so set x equal to 10, print x. Right, what's it going to print? Why did I say set x is equal to 10? Set x equals 1, so we know what x's value is. So print x, what's it going to print?
1.
1. X is equal to x plus 1. That increments x. Is x greater than 10 yet? No, it's just 2. So it didn't do go to 150. Else go to 100. Go to back up here. It's just going to loop forever. I've already made a mistake. And that's one of the risks of using go-tos, is it's incredibly easy to make mistakes. I would need to change that to go to 110. I could simplify the code a little bit by changing its logic to look like this. If x is less than or equal to 110, excuse me, why do I keep saying that? If x is less than or equal to 10, go to 110. I don't even need an else at that point. So here we go. Start over. 1, print it out. It's now equal to 2. Is it less than 10? Yes, it is. Go back to here. Print 2, add 1 to it. It's now 3. Is it less than 10? Yeah, sure is. Go back up here. Keep doing that. Finally, we'll get here. X will have been incremented to 11. It's no longer less than or equal to 10. It will not do that go to, and it'll print done, and we're done with the program. Clean, simple logic. Very seductive. However, if you have hundreds of lines of code, and you have a go-to statement, and you have multiple go-to statements, they can be going logically all through different areas of the code, including into blocks of code that you haven't set up correctly. Right? What if I did this? What if I didn't print done? What if I did this? 160 set y equals 10. 170 print y. You know, something like that. And then I had a go-to statement in here that went to 170. What, you know, as soon as we printed done, what if we did go to 170? Now, would you do that? No, this is just, but this is an illustration of an error. We printed done because we got through with that loop. We got here, we went to 170, print y. Has y even been defined?
No.
No, so it'll crash at that point. And that's the simplest explanation of an erroneous go-to, besides the fact that I made it go to this statement, you know, and it had an infinite loop. You know, I've already done 2 errors. One of them was intentional, the last one. Go-to leads to something called spaghetti code. Spaghetti code is where you just have go-tos and it's jumping to different sections in the code. You have 3 pages of code, you know, and you have 4 go-to statements, and just really hard to follow. And back in olden days, that's all you had as far as logical constructs, so you just had to be really good at this stuff, and you had to document it really well. But nowadays we have better ways of doing loops. I'm going to rewrite this in a way that a more modern language that supports go-to statements might do it. X is equal to 1, repeat. Print x, x plus equals 1. If x less than or equal to 10, go to repeat. Print done. Right. This skipped line numbers. And how did it do it? Instead, it has a label. And languages like C do support this. You can have a label, and you can use a go-to. But C++ and Java and C#, a lot of other languages do not even have go-to statements. Python does not have a go-to statement for this for the prevention of spaghetti code. But this works. You know, we set x equal to 1, we print it out, we add 1 to it, and as long, okay, that was dumb. Should have been 10. As long as x is less than or equal to 10, it would repeat over and over and over, and finally when x got too large, it would skip, you know, this would not happen, it would print done. Still would work. That's how you would see it. You may wind up being a C programmer, in which case you could see code like that. No code, no pun intended. So that's why I wanted to show it to you. But here's how it would be done in a language that supports loops directly. There. X is equal to 1. While x is less than 10, print it out, add 1 to it. And it'll keep running this until x is no longer less than 10. It'll print done. This is doing it without a goto. This is the Python way. The syntax is almost Python. If I did a colon there and I put a parentheses there, you know, if I formatted it correctly, then it would actually be valid Python, right, like that. It's called a programming structure, a logical construct, a loop. Ifs are also logical constructs. I'm not going to write this without. We'd have to do assembler in order to write something that just did not have an if-else logical construct. So, I'm not going to go into that. But this is writing it without a goto statement. It's preferable. It's far easier to debug like that. You can't write spaghetti code. I could be wrong. Don't try to prove me wrong on that by trying to deliberately do it. With a logical construct such as a while loop. There's another one called a for loop, which is even better. For x in range, starting at 1, stopping when you reach 11, adding 1 to it each time. Print x. Print done. Maybe you can see that that is pretty much way more awesome than that, right? When I say awesome, easier to read. Do they both do the same thing? Yeah. But I hopefully convinced you that using goto statements could lead your code to looking really horrible. It took a lot of discipline into writing non-horrible code with goto statements. The basic programming language had goto statements. You could use them, but it also had while loops. Pretty much anything invented after the 40s had while loops in it because they're very useful. And then the for loop is better still in a way. Because look at that, it just took 2 lines of code to print all that stuff out, ignoring the print done, whereas this took 4. Why was that possible? Why did it only take 2 statements? Because in order to do a while loop like that, you have to initialize the variable, you have to test it, and you have to change it. You have to update it. Those are 3 steps. The for loop initializes it, it checks it, and then it updates it all in one fell swoop, all in one line. You're defining all 3 of those steps. So your code becomes far more readable once you get used to the syntax of the for loop. Now, different languages have different for loop constructs, commands, syntaxes. You know, in C++, Java, it would look like this. For x is equal to x is less than or equal, or keep running while x is less than 11. X++ would be a different command. If I'm writing C++, it would look like this. Okay, good enough. Print this out like that. Same idea. You see the way the for loop works. Start it counting at 1. Keep running while it's less than 11. And then add 1 to it every iteration of the loop. Now, why did I make it 11 when I wanted to count to 10? Just because the Python syntax follows that. The way Python works is you specify a starting value, but your stopping value is 1 past where you want to stop. I didn't make the language. I wouldn't necessarily have done that. But that's the way that range statement works. And so I mirrored it. If I was writing this in any other language other than Python, and if I wasn't trying to match the syntax exactly, I would have done this. I like seeing, keep doing it while x is less than or equal to 10, because then I can eyeball it and go, well, I was going to start at 1. I'm going to stop when I hit 10. I mean, after I hit, you know. To me, that's easier to read, but you're going to see this syntax, so I'm not going to mention that anymore like that. But the same concept, that difference between 11 and a 10 doing the same thing, also takes place for while loops. If I wanted to make these bits of code match their logic exactly, I would have changed that to less than 11. It's still the same, right? Because 10 is less than 11, it would print out x. But 11 is not less than 11, and so it would print done. Same thing here. Once x, if x is still equal to 10, it's within that range. Y'all remember the terms inclusive and exclusive? The 1 is inclusive, it's included as part of the range. The 11 is exclusive. You just have to get used to that when you're writing these range statements. And you'll see examples in the book written in other languages other than Python, and they will probably do what I was doing with x is less than or equal to. So declaring and using variables and constants, performing arithmetic, the advantages of modularization, modularizing a program, hierarchy, charts, and features of good program design. Now we already know how to do that. We haven't defined any constants. The reason why is there are no constants in this particular language, but the idea is the same. What does constant mean? A constant is a value that shouldn't be changed, right? You define pi up at the top of your program, it should never change. What universe would pi change constantly? It'd be a pretty weird one. So the data type, when you declare your variable, every variable, and I think I've said this before, I'm going to say it again. I guess I better add some comments here. Illustration of using goto. Note, most modern programming languages, such as Python, Java, C#, do not have goto. So this is just an illustration of how you wouldn't do it anyways. So what was this? This was a loop to print from 1 to 10. Why did I start at 100? If you're writing a basic program, as long as the lines are one different, the line numbers are one different, you can start anywhere and stop anywhere, which made it useful because what happened if you wanted to go back in and insert some code between those two? You could tack that on. But nowadays, BASIC, you use Visual Basic or something like that. You use a more modern version of BASIC and you don't use line numbers on it. Why are line numbers bad? Because what happens when you've inserted more, say I needed to keep going, right? And so I go all the way from 111 to 119. But if I still needed to add more statements, that'd be a drag. Why? What if I had to go to 120, but I needed to fit in some there? I can't fit in anything there, right? Because I don't think anything supported fractional line numbers. Might be kind of cool. So you go, well, I'm just going to change that to 125 to give myself room. But then somewhere else, we had to go to 120. We'd have to spot where we changed it, right? I mean, where we had to go to 120 and change it to 125. I'm going to delete all that, undo those things. So, or in a language that supports labels, like the .command language that every command console supports, when I come here. And the bash scripting language, if you're a Unix or a Mac fan, also supports goto. So like the CMD or the C language. So this is the example of using a logical construct to handle the same thing. Using the while logical construct to do the same thing. Or using the for loop to do the same thing. A variable consists of 4 things. 3 of them are the most important in my mind because we don't see the 4th thing. A variable has a data type, and I'm pretty sure I've already said this. It's got a value. Oh man, my brain is already fried. The 4th one that I didn't want to, that I consider the least important, is it's got a memory address. I'm going to divert and do the guy in the box named Chip, since I keep forgetting to do that for y'all. Alright, and then what was the 3rd thing? The data type, the value, and the name. They all have a name. Okay. So when you do this, x is equal to 3. What's its name? Its name is x. What's its value? 3. What is its type? Well, we can't see the type in this particular language. In some languages, you define your type. You know, you say int, something like that. That would define it as being an integer. An integer is a whole number. But Python just infers the type based on the value assigned to it. A 3 is a whole number, and so that's a type of int. And then what is its address? We have no idea. It's just pointing to some address in memory. It's going to be different every time the program runs. They don't put the same, variables in the same address. It's actually kind of a security risk, because if you know exactly what memory address some certain value is always stored in, then you could write a program that would change those values. And so at a certain point, modern operating systems, including Windows, started doing randomizing of where programs are loaded into memory, so that even if you loaded the same programs into memory at the same time, the addresses would not be the same, the starting address in RAM. Okay, guys, so for the next 5 minutes or so, I'm going to be lecturing and drawing on the board. You guys who are at home aren't really going to see this. I apologize for that. I need to hook up the webcam so that I could flip between watching the board. Am I blind?
Your eraser's over there if you're looking for it.
Aha! Black on black. Good to see it. Thank you very much.
No problem.
Could someone sitting closest to the back go back there and hit the light switches to their max value? Otherwise, I'll do it. Other max. So sorry. Turn it to maximal brightness, because I'm going to turn this light off because it's got too much glare. I should have said that. Bad specs. I gave you bad specs. Okay. So, suppose we got a dude sitting in a box. His name is Chip. Har, har, har. He's the CPU. He's got an old-timey scroll of paper like the Romans used, but written on it are a series of numbers for all the way to gazillion, right? Whatever the length of our scroll is. He's got a hole in the box to where he can read any piece of data, and he can write with his pencil to any line number. And we make up a little language for Chip. We're going to say that if we tell him 11, that means he needs to read something. But you would have to specify where you want it to be read from. And if we tell him 12, that we want him to write a number. And that if we tell him, I'm just making these numbers up, 20, it means add. And then if we tell him 30, it means subtract. Something like that. We have 4 instructions in our code that he can follow. We're going to call those opcodes, just because we feel like making this example more complicated. These are opcodes. So he's got in his box with him a couple of little pieces of paper that he can write a number on. We're going to call those R1, R2, and R3. Those are actually registers, if you've heard of chip registers. There are things that the chip, they're little teeny tiny bits of memory that the chip can write to, and it's far faster for him to write and read from those than it is for him to reach out to the box. It's like if this could be done in 1 nanosecond, 1 billionth of a second, it takes 10 nanoseconds to do a read from this memory. So it's far faster to have registers here than to depend on that. I'm going to try to go somewhere with that idea. So we're going to hand him a piece of paper with some instructions. We're going to say, maybe I should write it over here. I'm just going to write some instructions down. And then I'm going to do this. mistake. I wanted that to be an 11. All right, so 12, la-di-da-di-da. Okay, so our little syntax here that I've come up with, anywhere I use R, I mean the registers over here. Anywhere I use a number, I mean a line number in his memory that he has access to. And apparently I made them all multiples of 100, so we're going to pretend that, you know, that his scroll is at least 300 lines long. Okay, so I hand him this sheet of paper. Do this, dude. So we have our program. His top line item. What is a command 12?
Right.
It's a write. And so we're going to tell him to write the value 3 on the line number 200. So these are the addresses. I'm going to write the values of them out to the side. And then we have another write. We're going to write to memory address, and we're going to write the value 4 there. And then what is an 11?
Read.
11. Read the thing on line number 200 and write it into address R1, into register R1. So what is stored at address 200?
A 3.
A 3. So he's going to have a 3 in that box, in that register. And so then Chip reads the next line of the program, which is also a read. Read from that address and write it into R2. So he goes down and he looks at 300, he finds that value and he puts it into register 2. Then he gets to a new style command. What is a 20 in our code?
Add.
That's an add. So he's going to add R1, add 2, and write the results into R3. So a 3 and a 4 added together, 7. His last command in this program, 12, which we said write. Write whatever's in R3 out to 200. So we come and update this. Well, R3 wound up being 7. And then maybe we would print, you know, whatever was at that address or whatever. But, you know, he doesn't have a way of printing at this point. He doesn't have a way of doing anything else other than reading and writing. But so this is the way that a CPU ultimately works, a microprocessor. The transistorized things that were invented in the 60s that created, you know, the computer revolution. Before that, of course, you had electronics that did this, but until the invention of the transistor, you couldn't shrink a computer down into a single chip. So these are the opcodes that work for this particular chip. Every different chip style from different companies had its own series of opcodes. There were Motorola chips, they had completely different opcode sets. You know, you had Intel chips. Why did they come up with different ones? Because they were each one was trying to come up with a chip architecture that was the fastest, the most powerful, the one that could address the most RAM or whatever. Nowadays, there are whole bunches of Intel compatible chips. But your phone probably doesn't use an Intel chip. It probably uses an ARM processor, ARM, which was invented originally by a game company in Britain, or a computer company, just like Commodore was in the United States, and all those Atari and all those early computer companies. Acorn was the popular one in Britain, and they came out with the ARM processor rather than wanting to rely on Texas Instruments or Intel for their chips. And you know, got updated a billion times between the 80s and whatever, but it was a really low power, fast processor, which made it perfect for phones. You don't want a big, heavy, power-sucking chip in your phone, and you don't get much battery life. So most portable devices use the ARM processor. Most computers use an Intel or Intel-compatible processor, like if you buy one from AMD. So that's the real point of this, is to just show you that all a program does, ultimately, is it's a series of commands that access memory. Now, there are special parts of memory and special things that happen. Like if he wanted to send something to a printer, he might have to write it to a special address. Or if he's going to talk to the video card, he may have a separate memory to write to. And so this is done via a bus, the RAM bus. And And writing to the video card is done by what's known as another bus. Bus is shuttling data back and forth. And then if he wants to save data to a disk drive, he writes to the bus that sends things to the disk drive. So note that if it took 1 nanosecond for him to access a register, these numbers I don't know, and if it took 10 nanoseconds to read from RAM, it might take 100 nanoseconds or 1,000 nanoseconds to read and write from the disk. So if the contents of your disk, if you load that file that you want to access into RAM, and then you start doing stuff from it, you make a far faster program than if you hit the disk drive every single time. And nowadays all that is handled automatically because disk drives have caches in them, caches, so that you don't actually have to spin that magnetic media, wait for the thing to get under the head so that data can be read in. And then you have a disk. Used to be a spinning, now you have solid state disks which don't have any moving parts. So those are faster. Might not be 100 nanoseconds to pull data out of that. It might be only 30 or something like that. It might be something far faster in order to do that. But there's lots of places for this slowdown to happen. There's lots of places for speed improvements. Your earliest computer might not have had a RAM cache that could load stuff into some special fast memory. And then nowadays the chips have their own cache, so that frequently used addresses in here are stored here so that they can be used even, accessed even faster. When you write a Python program, it is ultimately compiled into a series of opcodes, also known as the binary code, also known as the object code. And this is what actually drives the computer. Or a simple explanation. Good old chip in the box. Does that kind of make sense? Now, if you're an electrical engineer, you may be going, well, that was a dumb explanation. But if you've never been introduced to the concept, I left off some pieces. There's going to be a clock, which is sending pulses to the chip. Each time he gets a pulse, he knows to go to the next command. And you gamers may have had computers where you overclock the chip, make it run faster. What was the risk of overclocking your chip?
Overheating?
Yeah, he could overheat. He's working faster and faster and faster. You have a heat sink on your chip in order to radiate that heat. Nowadays chips run incredibly hot because they have billions upon billions of transistors in them, each one trying to do work. All right. So heat dissipation is actually a really big problem in computers. For example, those server farms that Google and Amazon have, where you store thousands of computers in a single building, you have to have some seriously heavy-duty air conditioning to keep them cool. If your computer overheats, it stops working. I don't remember if I posted the link. Did anybody manage to watch the video that I wanted y'all to watch? If I didn't post the link, then
I didn't see.
You probably
the
didn't.
video.
Right. I put it in the notes. That wasn't very obvious. I need to remember to go and put it right in the notes in our announcements. It's never a bad idea to go back and look at the notes for the class again, even if you wrote them all up yourself, because I go and I prettify them, I put tables and stuff like that.
I see that.
Apparently I didn't put the link to the video in here.
Yeah.
There it is. Alrighty, why don't we post that in our announcements. I do want y'all to watch this. It's not like I'm going to grade you on it, but I do want you to watch this, and it's only 10 minutes long. Yeah, not a video I made. Okay. This is a really good series of videos to watch, so I may be linking y'all to other ones that I want you to watch as well. All right, so that's just in our announcements now. In our program, it was kind of lame that we were having to address memory by the address number. Write to address 200, read from address 300. That's the way computers worked in the 40s and the 50s, but then with the invention of programming languages, you wanted the idea that you could just give an address a name and then forever after refer to it by that name. Right. I don't want to have to say memory address 200 if I could just give that memory address a name and call it X or pay rate or pi or something like that, so I wouldn't have to remember where I stored the value of pi every single time. So that's what it means when it says that a variable has an address, or that's what I mean. So every variable has those 4 components. We don't see the address. Some languages let you get to the address if you want to figure out what place it is. Most, I don't know how to get the address of a variable in Python, and even if you had it, what could you do with it? So these are the things I really want you to remember. Data type, value, and the name of the variable. Well, we could come up with another, What is his name? His name is, okay.
Thing's not turned on. We can't see what's on.
Yeah, y'all are having a good time watching my non-existent monitor.
Right? It's a very nice shade of white.
Change this. Okay. So, what's the name of that variable? X. What is its value? 3. What's its type? Ints. We have like 3 types that we're going to be starting with at first. We have ints, which are whole numbers, integers. We have floats, which are numbers that support floating point with exponents. So, floating point numbers. They support fractional values, not just whole numbers. They're stored in a completely different format in the computer, and they're not precise, right? Because if you do 1 divided by 3, what is 1 divided by 3? It's 0.333333 out to some, very large number. But what is 1 divided by, you can't store an infinite number of 3's in memory, or else you run out, right, of RAM. So if I do 1 divided by 3, okay, here's a typical usage of it. That may be 8, 10, 9, 11 digits. Looks like 11 digits of accuracy. So all floating point numbers have some limit to their number of accuracy. And what's worse is that they are actually stored in binary rather than decimal, and so further rounding errors can occur. 0.3 cannot be stored precisely in binary, just for reasons I'm not going to even talk about. Floating point numbers can give you rounding errors, and they're not 100% accurate. Integers are wholly accurate because they're just whole numbers. Does that mean you're not going to use floating point numbers? No, because they are very accurate, and they're the only way to solve vast numbers of problems. So, those are 2 of our types, and the third type is the string. The string is, words, text, series of characters. What is a character? It's a single character, a byte, an ASCII value, or a Unicode value. So that's another type that you could have. Python doesn't really have a separate data type for characters, so I may leave that off. And then there's the bool, or the boolean, which is just a true-false logical value. You could say x is equal to true, and then you could do if x, and it would do whatever it was supposed to do if x was equal to true. All right, so we could do a variable called hungry. Am I hungry? No. I skipped city. The name of that variable is Hungary. Its value is false. Its type is Boolean. How about this one? City. What is its name? City. What is this value? Tulsa. What is its type according to the 4 types I listed up there? Is it an int? No. Is it a float? Come on, guys. What did I say? A series of characters of text. Yes.
String.
It's a string. Right. In Python, you put quotes around it. In Python, you could use either apostrophes or single. You can use double quotes or single quotes. Why do I specify that? Other languages force you to use double quotes, and single quotes have a different purpose. Okay, so those are the 4 data types that I consider really important at this point. And then, like, you might have one called temperature, which is equal to 98.6. And so what is the name of that variable? Well, why did I make it so long? I don't know. Temperature. Why don't I just call it temp? Easier to type. Alrighty. And what's the value of that one? It is 98.6. I'm almost belaboring this too much. And then what is its type? According to my 4 types up there, what do we... That's not an integer, is it?
Float.
Yeah, it's a float. All right. So there we go.
So float is basically anything with decimal, right?
Right. Even if it looks like it's a whole number, if you do x is equal to 1.0, well, that's a whole number, so it's an int. No, as soon as you type that decimal point, it makes it a float. And it is stored in memory separately. And floating point math is a lot more difficult than integer math for a computer. That's why there used to be things called floating point coprocessors. You'd buy a separate chip to put in your computer, and suddenly you'd be able to do floating point math faster. So your games could run faster, or your scientific calculations could run faster. Nowadays, of course, those are bundled into the chips themselves as part of the chip design. Alrighty, so we've got our 4 types, 4 variables. Looks like I wound up using 5. In Python, you can mix and match the data types. It's okay to do this. X is equal to 1, X is equal to 3.4, and then turning around and saying X is equal to, 1 like that. Python will make that variable change according to its type. That's an int. What is that one? I already typed the F, gave it away. Bad. And then what is that one?
That one's...
That would be a whole number or an integer.
That is a string. Looks like an integer. Looks like an integer, but it's got quotes, so that forces it to be a string, which is also stored completely different than the other types. It's stored as a sequence of bytes. So we can't do math on this at all. Even though it looks like a number, can't do math on it without converting it to another data type. Yeah, and when we convert it to another data type, what if it wasn't numeric representation of data? What if it was an A or the word Fred? That couldn't be converted at all, and it would be a very, it would be a problem to the program that it would have to handle. In some languages, once you declare a variable, you can't change its type on the fly. If I did this in one of those languages, if I said int x is equal to 1, and then later on I went x is equal to 3.4, no, that's not going to work. It was defined as an int. If it doesn't consider it a syntax error, at the very least, it's going to round it down to fit into an int. That's what the C and the C++ programming language do. A lot of languages just flat out do not allow that because we are losing data, right? We lost that 0.4 in the conversion to an int. So this is what's known as a strongly typed language. This would be an error. And so would this. Because x was declared as an int, it has to stay an int. You can't magically put in a string into memory that had been dedicated to storing an int in those languages. Those are strongly typed languages. Python is not a strongly typed language. It's a weakly typed language. Type meaning the type of the variable. Variables can be redefined on the fly. And in a strongly typed language, a variable, once created, can only hold data of that type. the book was originally written for strongly typed languages. It was only the newest version that supports Python. So if the book makes references to data variables only holding one data type, that would be why. And you could make that a law in your programs. You could just say, once I declare a variable as an int, I'm never going to use it to hold a float, or I'm never going to use it to hold a string. Now Python, by and large, makes it so that ints and floats can be used interchangeably in the code. Meaning that if you divide an int by a float, or a float by an int, or an int by an int, or a float by a float, it's not a problem. It doesn't care. More strongly typed languages will give you different results if you divide an int by a float as opposed to dividing an int by an int. So in Python, we don't really care too much about whether something is an int or a float, except for the idea of rounding errors. If we can do something with whole numbers, that's better than typing that, making that variable a float, and then introducing the concept that all further operations on it will keep it as a float and introduce the idea of rounding errors. I'll try to come up with an example of a Python rounding error just so you can see it in action. You can see how you can get improper results of your program by having the wrong data type, or just you have to accept that you can have rounding errors. Okay, so, and along with these, each one also had a memory address. X was stored at some memory address, city was stored at some memory address, but we don't know what those are, so I'm not going to write a column for memory address. So all programming languages support these data type. Numeric are numbers that can be used in math, which a lot of them break down to ints and floats. You could write a language that everything was a float. Strings are anything not used in math. Early computers didn't even, not everything used binary to hold the numbers. You could code in decimal values and do decimal math, but it turns out that that's a far slower process for a chip to do than to do binary math. So nowadays they all use binary to encode their data. Two types of constants. What is a constant? It's a number that can't be changed while the program is running. I'll give you an example of that. If I say x is equal to 3, 3 is an unnamed constant. It doesn't have a name. But nothing's going to change that 3 unless you go in and edit the program. Right? I mean, that 3 is a 3. A 3 is a 3 is a 3. So it's called an unnamed constant. Some people refer to them as literals. It's literally typed into the code. I don't know why they were called literals. Which does the book call them? The book, I believe, just calls them unnamed constants. Oh, they call it literal. Okay. So a numeric constant then can only hold numbers. A string constant, also known as alphanumeric values because they can hold both letters and numbers, are declared using quotation marks. So I'm just going to say that an unnamed constant is a number typed directly into the source code, or a number or string. Right? 3 is a named constant. All of these are unnamed constants. Tulsa is an unnamed constant. False, well, that's a keyword. 98, but it is constant. You can't change false to mean something else. 98.6 is a constant. 1 is a constant. Fred is a constant. All of those are unnamed constants because they can't be changed. You can call them literals. Now, some languages support the idea of named constants. A named constant is a variable that can't be changed once assigned. Right? So if I do constant pi is equal to 3.14159, then the program would give an error if later on in the code I decided it was equal to 3.1. I should not be doing that anyways, but There are examples of other times when you might declare a variable. You don't wish the program to ever change that value. Now you might just say, okay, never change the value of pi, please. Thank you very much. You know. But if you're working in a team, somebody else may not know that they're not supposed to change that variable. What if you declare a limit, you know, RAM limit, and your program is not supposed to use more than 64K? And it's really important that that limit never be changed while the program is running. You can declare it as a constant. Constant RAM limit is equal to 65536. And that way, another programmer, if assigned into it, they might think that it's okay, you know, halfway through, that if the program needs more memory, that they could change that. No, you better change it at the place where it's defined so that it's the same size all the way through the program. So that's the idea of a constant. It's a number that should not change, or it's a value that should not change while the program is running, except when it is initially assigned. C, C++, C# have a keyword for that called const. Java has a different keyword, I don't know why they picked a different one, called final. That's its final value. It's its final answer. The RAM limit is 65536. The only way to change that RAM limit is to go in and change the source code. If you're writing the source code and you try to change the RAM limit halfway through after it is defined, it would give you a syntax error to let you know that that was wrong. Python doesn't support constants. Kind of too bad. So, there's a gentleman's and gentlewoman's agreement. Any variable defined in all caps is treated by programmers as if it were constant. So if you're handed code and you see a variable that's in all caps, you know that you're not supposed to change it. Even if the language allows you to change it, you're not supposed to because it was declared in all caps. Am I going to strictly follow that? If I type in capital X is equal to 3, it probably doesn't mean that I want X to be a constant. If I type in capital L is equal to, and I make a list of values like that, it's not because I wanted that to be a constant. It's because I wanted to dictate that it was a list. I should have used a lowercase letter there, but if I use a lowercase letter there, it kind of looks like a 1. Or maybe to the people in the back of the class, it looks like an I, right? Can't tell whether that's a capital I, a 1, or a lowercase l, all that stuff. So just for clarity, I may use that. L. But otherwise, all lowercase things are variables, all uppercase things are constants. Now there's no law. It's an unwritten agreement, or it's a written agreement, right? You see a variable that's written in all caps, you know that your program isn't supposed to change it. Why am I going so much on that? Because the book talks a lot about constants. And then we don't even have the ability to assign constants in this language. Does that mean that Python is dumb? No, it just means that the designer of the language decided not to make constants. Python is an extraordinarily powerful language that is used by a whole bunch of people for serious problem solving. It has its uses, but there are things that it's not so good at. You wouldn't write video games in Python because it's not a fast language. The reason why it's not a fast language is that it doesn't get compiled into an app. It doesn't get compiled to an exe by the programmer. It's distributed as source code. You have to give somebody this English-looking code, and then they have to run it, and then it gets turned into machine language on the fly every single time they run it. That's a slower process. That's called interpreting. The code has to get interpreted at runtime. Python is not the only language that does that. JavaScript does that. But there are other languages that do compile to .exe, such as C and C++. They run very, very quickly because they've already been turned into machine code by the programmer, and you get not the source code. When you download Call of Duty, you're not getting the source code, right? You can't go in and see all the variable names and stuff like that. You're getting the end result. You're getting the machine language, and so it runs far more quickly. So most video games that I know of are programmed in C and C++ just for reasons of pure speed. Even if the programmers didn't like the language, that's what they're going to use if they're going to program that kind of stuff. And I'm just using games as an example because we know games need to run as fast as possible to be fun. But, you know, stuff like applications that run on your desktop, Word and things like that, they're probably written in C++ as well so that they'll run fast. You're really annoyed if your word processor is sluggish. Computers being faster and faster and faster all the time, people are moving to using interpreted languages even for stuff that your computer that in the past would have been written in a compiled language like C++. For example, when the Surface computer was first introduced, there were two kinds. There was one that was purely Windows compatible, and then there was another one called the RT that was not Windows compatible. I don't know why they did that. It ran software that looked like Windows, but a lot of the programs in it were written in scripting languages. Don't know why. They dropped that one from the lineup very, very quickly. Surfaces are really awesome little laptops. Okay, but I wouldn't have wanted one that was not Windows compatible. It's almost going to be time for a break soon, but we're going to go a little bit further. So constants. The values don't change. Literal constants are the numbers and the strings that you put in quotes. Named constants are the ones that, you know, are stored in variables. So variables are named locations. Their contents can differ. They can vary. That's why they're called variables. The declaration is a statement that provides a variable. It gives its data type. It gives its identifier. Optionally, it gives an initial value. If you look at the pseudocode and the flowcharts in this text, they will have an entire section set up for declarations. They may do something like this: start and then declarations, you know, and say I'm going to write some program that's going to calculate, you know, your body mass index because, you know, you want to see if a population is, you know, population of India is heavier on average, you know, than the population of the United States. So anyways, you might declare your variables. Alrighty, so height, set height equals to, you know, say we're going to do it in inches, 72 inches. And then set weight is equal to, you know, and then say that we're going to, you know, I'm going to say this person 6 foot tall is 200 pounds. All right, those are our declarations. I may not have the syntax exactly right, but that's the advantage of pseudocode, is you don't have to get the syntax exactly right. And then later on, after your code, you can start doing stuff. You know, you could print, and then whatever the equation for the BMI is. I'm going to skip right in the whole thing. Height divided by weight, whatever. Okay. Except pseudocode would have called it output, right? And they wouldn't have necessarily used the parentheses. Okay. So that's a real simple little program. It's no different than what we would have written. We would have stored this variable, set ratio. Now in a strict programming language where you have to define every variable before you can use it, we might do that, and then later on we use set ratio equals to height divided by weight. If you've done the homework assignment or the first one, or if you remember from the other, this looks real close to our pseudocode, except it's broken out a little bit more. We have a section for declarations. Some languages require, not anymore, very, very rare now, that all your declarations happen at the top of the block of the code. That you can't just suddenly declare a new variable. By and large, the vast majority of modern languages do not have that restriction. It's nice to be able to declare a brand new variable on the fly, you know, when you need it, so that it's close to the place. And if that was the case, I might not have declared this right here. I would have declared it right then and there on the spot. Why am I saying all this? Because you will see a section of your pseudocode in the books where they have a section called declarations. And in the flowcharts, similarly, they'll have a block for declarations. And it's kind of cool to use a declarations block in your flowchart because otherwise you have to define each set in its own block. And it's kind of nice to be able to cheat. Write one block and it has all the declarations in it. Saves you from drawing, 3 blocks better than 1. But when you declare the variable, you're giving it a type, and then you're giving it a value, starting value. In this language that we're using here, the type is determined by the starting value that you give it, or by the value you give it no matter what. Alrighty, I'm going to go 5 more minutes and we're going to start our break. No, actually, why don't we stop here? Let's come back here at 1:30. So if you need to run out to the car and get a jacket or you want a Coke or whatever. For this. Alright, this semester is being blessed by lots of MindTap problems. Firstly, is that the demo period, trial period has already expired. Secondly, for some folks, MindTap is not opening in a separate window. It's not saying cengage.com when you click on the MindTap link as it should. Instead, it's saying D2L. Or if once you've purchased it, you can't open MindTap from the links and content, buy it at this link and then access it here. So give that a shot. See if it'll. No, go to the announcements page or just click on.
Yes, I just got one.
Scroll down, buy it at this link.
And then when we said I'm going to go through that option only.
Right, you're gonna go through the alternate link. So, the declarations, notice as I said, the book shows putting all the declarations in a single box. And they're just using the word num in front of them. I don't care how you do it. Set, num, whatever. Here's a couple nums, and then later on we're going to input my number, we're going to use my answer, and then we're going to output my answer. And here's a pseudocode variant of it. Declarations, num and num. I guess I'll go and modify mine to be exactly the same as what the book is showing. So a numeric variable can hold digits. Our language and many of them have 2 types, int and float. You can perform math on those. A string variable can hold text, it can hold letters of the alphabet, hold special characters, but you can't do math on it without converting. And that's why in our Python code, when we were doing it, x is equal to float x, that kind of thing. Convert it to a floating point number so that then we could do math on it. Type safety prevents assigning values of an incorrect data type. Our language doesn't have type safety. A lot of them do. Just have the concept tucked in your mind, is that in a lot of languages, once you declare something as an int, the only thing you can store in it is an int. If you feel like abiding by that idea in your Python programmers, I encourage that. On the other hand, when I do x is equal to input and then x is equal to float x, I've already violated that idea. Why? Because x was a string after the input statement, and then we did x is equal to float x. That turned it into a floating point number. So I don't strictly abide by type safety in this language if it makes the code easier to read. An identifier is a variable's name. You're supposed to choose reasonable and descriptive names. Single letter variable names are for the birds. We shouldn't use them. On the other hand, when I'm typing in examples here, single letter variable names are great just because you're probably typing in the notes, or if you're typing along, and I use variable names like patient _ temperature. That's way too long, especially when we're actually trying to write code and we're in a hurry, and then people are going to be misspelling the variables. Not so much of a big deal when you have when you have lots of time to write this stuff. Pick good variable names. You don't have to make them super long, but like if you need a patient temperature, T, that's a lousy variable for temperature. TMP, that's still a lousy variable. It looks like, temp,
these look like temporary variables. PT? Nah, these are all bad. Ptemp? How about patient temp? Patient temp, patient, underscore, temperature would be even better. Or at the very least, temperature, you know, that kind of things. Now in our programs, when we were inputting, the, you know, converting from kilograms to pounds, you know, input kilograms, pounds is equal to kilograms. That's enough. You don't need to spell out the whole word kilograms and the whole word pounds. You know, those are clear. But in general, these are kind of bad variable names. These are kind of good variable names. The computer doesn't care. You could call each variable Fred1, Fred2, Fred3, and Fred4 as long as you use those consistently in your calculations. Avoid single letter variable names, except for counters. And demo code, like what we write in here. Variable names should be, and the book calls them identifiers, should be descriptive. You're not only writing code for yourself, you're writing it for the other person who's going to come up and look at it. In this class, it's me. In a work environment, you know, your coworkers or whoever you're going to sell your code to. They need to be able to look at the code and understand what it's doing. And if you have bad variable names, single letter variable names, or X1, X2, and X3 all strewn throughout it, they're not going to be able to modify the code. They're not going to be able to understand it half as quickly, a tenth as quickly. So it's called self-documenting code. We've had these comments. The comments document the code by describing what each section does. But good variable names also are a form of documentation just because they make it clear to the person looking at the code what they are, what they do. So, you can use letters and digits. Some languages allow hyphens. Nah, I've never seen. Underscores are the way to go. So, rules for identifiers. Letters, upper and lowercase. Digits, 0 through 9 obviously. Underscore. Names can be a mix of those. Can't put periods in them. Can't put spaces in them. Some languages let you use dollar signs, but that's not a universal. I wouldn't bother trying to put a dollar sign in my variable names. And one more itty bitty rule, names cannot start with a digit. So if I asked you for 4 rules of naming variables, those would be them. I could type up some variable names. Patient temp, P temp, P underscore temperature, P dot temp, you know, tax rate for 2018, 2018 tax rate, 2018 underscore tax rate, stuff like that. Which of these are illegal? Is that a legal variable name or an illegal?
It's legal. The last two aren't legal.
This one is illegal because it's got a space in it. How about that one? I kind of said don't use ptemp, but it's certainly a legal variable name. Not necessarily a good one, right? How about that one?
Good.
Yeah, that one's good. Underscores are cool in most languages. What's wrong with that one? It's got the decimal. Now, at a certain point, you're going to see variable names that look like they have decimals in them. But it's not really a decimal. It's a variable that's attached to another variable. So if I do like mouse rate, it means that there's a mouse object, how fast the mouse is moving. And mouse.x is its x position, and mouse.y is its y position. That's actually legal. in the languages that support that nomenclature. But these aren't variable names. This is the variable name. This is the variable name. This is the variable name. And this is the object that it's attached to. And that's the object that it's attached to. And that's the object. But we're not going to be talking about that. We'll see that, though, at a certain point where maybe we'll do it right dang today, because I don't like doing an entire lecture without giving us a chance to code at least a little bit. But let's keep going. What I want to do is I want to use the Turtle library to draw pictures on the screen pretty soon, just because that's illustrative of programming concepts like loops and things like that. Did it let you in when you did it that way? Were you able to purchase it if you were?
Yeah, it's all good now.
All right. Okay, good. If I didn't want the MindTap integration of it copying the grades from the homework, and the tests automatically, I should just do it the alternate way. I may switch over to just doing it that way because of the problems of D2L integration. However, D2L is being phased out. At a certain point, we'll be using a different online learning management system, and maybe MindTap works better with that. Maybe I'll vote that we stop using it entirely. Let's onward and upward. They are case sensitive. They do have to be one word. They must start with a letter or an underscore. Some people use underscores at the beginning of their variable names to mean something very special as part of object-oriented programming. It's not real common. The Python programmers sometimes do it. Other language programmers usually don't. And they should have a meaning, an understandable meaning. All right, naming conventions. Camel casing is when you use an uppercase letter in the middle. Pascal casing is when you use a caps at the beginning and then any other word in the variable name are also capitalized. So like in camel casing, patient would all be lowercase, but then T, temperature. T would be capitalized. Don't use Pascal casing. Nobody uses that. And then there's Hungarian casing. This got popular because Microsoft did it, and maybe they still do, and so a whole bunch of books and code examples, in the early days of Windows and stuff like that, use this kind of example. The idea behind so-called Hungarian notation, invented or named that just because the programmer at Microsoft who first came up with it, was from Hungary. You prefix the variable with the data type. Some people shorten them. I means int. S means string. Or SZ means, a Z terminated string. Or an F is a floating point number. Yeah. I don't recommend y'all do that. Just tuck that name away in your brain in the far future. If you go and work at a shop that follows Microsoft naming conventions explicitly, then you may run across that. And the idea is that all the ints will be prefixed with an I, and then if it's a pointer to an int, it might be a PI, and then if it's an array of ints, it might be AI. That people come up with these very specific things. And then, I'm not going to even talk about why you might not want to use it. Simplest is that it just creates longer variable names, which are not necessarily the easiest to read. Snake casing, underscores. This is what people did like in the 60s and the 70s and the 80s before camel casing became the popular thing. Some things are just fashion. I like underscores. One reason I like underscores is because as soon as I start mixing uppercase and lowercase, y'all start typing them in wrong. I start typing them in wrong. Nothing wrong with y'all. But an underscore is real easy to see, right? So I tend to use snake casing. Am I going to call it that? Probably not. And then mixed case with underscores. Yeah, whatever. Kebab case, dashes. Well, I don't even know languages that support dashes because dashes usually mean subtraction. Oh, wait, I wish I could disable little tips. I guess if I was viewing it in full screen presentation mode, it wouldn't do that. But anyways, certainly I'm not going to use that because a hyphen means subtraction. Okay, assigning a value to a variable. It's called the assignment operator, the equal sign. The equal sign is used to copy a value from the right-hand side and store it into the variable that's shown on the left-hand side. So we're going to cover a couple of different terms that are all very similar. You can have a declaration, int x, and then you can have an assignment, x is equal to 10. And then you can have what's known as initializing, which is int x is equal to 10. Python doesn't even make you declare the type. It doesn't have that option. So, what we usually call is the first assignment the declaration. And it's also a form of initializing. And initializing is when you declare something and you give it a value at the very beginning. So I will be using the term initialize and declare as synonyms in this language. The first time you create a variable is declaration. The first time you assign a value you can call that initialization. In Python, every declaration is an initialization because there's no separate giving a variable of a type. So, kind of can use the words loosey-goosey interchangeably. Now when you're taking the test in MindTap and it asks you for the difference in initializing and assigning, give the book answer. Otherwise, I'm not going to ask that in any of my quizzes or exams. But when I'm writing code or pseudocode, I'll say we'll initialize x with 3, or I'll say we'll declare x. And those two statements might be the exact same thing. Set x equals 3, or assign 3 to x. All three of those things start to sound like they are the same. If you get very, very, very picky about it, the textbook definitions are different. All right, so the binary operator means it requires 2 operands, not binary as in zeros and ones, but binary as meaning it requires 2 operands. There's more than one kind of binary operator. Binary operator requires 2 operands. I'm putting quotes around the term operator and operands because those are special words. An operator is a symbol. Addition, subtraction, multiply, divide. Floor division, our language supports floor division, which means do the division and then round down. Modulus, which means remainder of. Less than, greater than, less than or equal, greater than or equal, 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 equal. All of those things are binary operators, meaning that they require 2 operands. Operands are the pieces of data on each side of it. 1 plus 2. Plus is the operator. 1 is the operands. So, Python supports a lot of operators. I listed a goodly majority of them there. Is every single operator in existence a binary operator? No, some languages have something called the ternary operator, which requires 3 pieces of data rather than 2. Some people refer to the minus sign if you're making a number negative, like if you're saying x equals -3, they say that negative is a unary operator that takes only 1 piece of data. We're going to just run with binary operators, and we're going to remember that they require 2 operands. X equals 3. Equal is the operator. and x and 3 are the operands. Technically, the people call, when I say people, the computer scientists who invented all the terminology, call the thing on the left-hand side of the equal sign the L value. And in some languages, you'll get errors if you do something wrong, and it'll refer to the L value. Syntax is important. X equals 3 is good syntax because the L value has to be a variable. 3 is equal to X is bad syntax. Why? Because 3 is a constant and you can't override it with the value of X. That'll give us a syntax error. The syntax error that we get may refer to L value or something of the effect. Let's remind ourselves of what idle does in that case. So I'm going to launch idle, and right in the shell, I'm just going to test it out there without even writing a program. I'm going to say X is equal to 3. That's great. And then I'm going to type 3 is equal to X. That's the syntax error. It didn't mention L value. That's too wonky. That's too, nerdy. Instead, can't assign to a literal. Okay, literal is also kind of wonky, nerdy, but we've already established that a literal is a number, a unnamed constant. And so the variable has to go on the left. And I'm making a point of that because on exams, even though you will write code for a month that does the assignments the right way, I will have 2 students who'll flip them and have to go, well, I can't give you points for that. All right, just remember that. So initializing a variable is giving it a starting value. Your salary is $14.55. Your name is Janita. Garbage is a variable's unknown value. Our programming language doesn't support garbage. But in the programming languages that do make you declare your variable before you use it, like int x and float f, if you don't give them, if you don't initialize them with a value, if you don't assign a value to them, then you don't know what x is. You don't know what f is. You try to do a calculation with it. At the very best, the compiler won't even let you do a calculation with x or f, right? If you do print x, that should be an error. That should be a syntax error. Some languages, some compilers might not give you an error there, but whatever x is just some random contents of memory. Whatever was in that memory address before x was declared, whatever it's pointing to. Who knows what's in that memory? So you're going to get a crashing program at the worst, or you're going to get at least a program that gives out, wrong answers, wrong results. So you can't use an uninitialized variable. Python doesn't let you. Python doesn't have the idea of garbage variables. A lot of other programming languages do. Sometimes I wonder if we should teach this in another programming language, but the syntax of Python is so clean. If you're going to write C++ programs and Java programs and stuff like that, you have to put a lot of boilerplate in it just to write the simplest program. The simplest program in Python is print hello world. Here's the simplest program in C++. # include iostream using namespace std int main cout hello world. Okay, great, huh? It took 6 lines. Oh, and I forgot one. Return 0. That's what the simplest program looks like in C++. Here's what it looks like in Java. Class myprog. And you don't have to type these notes in, but I just want you to get the idea that different languages have completely different syntaxes that have common elements. They all have the same ideas of doing math and doing input and doing output and writing to disk and displaying information. Okay, and then void main, I'm going to simplify that slightly. and then system.out.println hello world. Maybe that's a little bit better than the C++. Something to note about that C++ program. And do I want you to memorize all this stuff about C++ and Java? No, but I'm hoping that this isn't the last programming course that you take. I would totally dig it if all of y'all would take Java over the fall, preferably for me. You may not like me, you're free to take one from another instructor, or take my C++ class. Those are good follow-ups to this class. You will learn a completely different language. All the concepts apply, though. The idea of loops and assignments and variables and data types and floats and ints and output and input and write into file, all the concepts are the same, but they introduce new concepts as well, and their syntaxes are different. One thing to note about the C++ is the hash doesn't mean comment. C++ and Java comments are // Okay, but when we're learning program, wouldn't we rather just do that? Right? So that's the Python version. Don't memorize the C++ and Java. Unless you want to, I can't tell you what to do. You're not the boss of me. And it's just there to compare. And the book has examples in all these different languages. It's not a bad idea to at least be able to recognize components of these languages as you go along. The way if statements are written in one language, in some languages they require parentheses after the if statement, and others they don't. Python doesn't. It's an example of the language syntax being simpler. Why is it simpler? Because the guy who wrote it wanted to make it simpler. And he built, you stand on the shoulders of giants when you're writing new things in programming, because, lots of stuff has already been invented. Those old syntaxes had already been invented, and he thought he could do better. And in many ways he did. So declaring a named constant is similar to a variable, but it can only be assigned a value once. You assign a useful name to the value that will never be changed. Pi equals 3.14159. What is a magic number? A magic number is one that you just don't understand. No, I won't say you don't understand it, but it appears out of nowhere. Right? If I do this, if x is less than 1024, print something. Right? I'm not going to know what 1024 is. Why in the world did I throw a 1024 in there? You have no idea if you're just opening the code, right? I know because I wrote the code. 1024 is a magic number. You would have no idea why I chose 1024. You would have no idea the consequences of changing it. You use constants to avoid magic numbers. So if you put list limit equals 1024, and then I could write the code later, if x is less than list limit, do something. When you're reading the code, that's a lot clearer, right? Because they wouldn't necessarily be together. This could be pages down in the code. Or it may even be in a separate file. If your language supports the idea of header files, this may have been defined in a header. So this avoids the use constants to replace magic numbers. Does that mean you have to avoid all literals? Do you have to avoid all magic numbers? No. What is the formula for calculating the area, the volume of a cylinder? The volume of a cylinder is equal to height times radius times, but that was a bad example because it doesn't have any magic number. How about the volume of a sphere? So it's equal to 4 divided by 3 times the radius to the power of 3 times pi. That's that formula. Well, that 4 and that 3 and that 3 are magic numbers. I better, declare constants for all of them. Nah, it's math. Yeah, that's a good idea to put a comment. Formula for volume of sphere, right? Magic numbers aren't always bad. Literals are not always bad. X is, if you want to add 1 to it, x plus equals 1. You don't have to make 1 a constant and declare that elsewhere. That's getting ridiculous. But if it's a number that has meaning that is not instantly understandable, and not just part of a math formula that you can look up in a book, an example of that would be sales tax, right? Price is equal to, or the total is equal to the price times 1.00 plus some state sales tax. I'm making these numbers up. You know them exactly, and I don't. Okay, plus. Okay. Whatever. Say that's Midwest City's own personal sales tax. That could be, you would calculate the total price. Looking at the code, you don't know where the .00623 and the .00100 are. Those are in effect magic numbers. So it would be better to do something like this. State tax equals .00623. City tax equals .00100. And then you could do total is equal to price times, and then the same thing, 1.00 plus state tax plus city tax. That's clear, right? Because again, this might be pages down, way down in the guts of the program. You might see that. There's 2 reasons for doing that. 2 reasons for using named constants. 1, avoid magic numbers mysteriously appearing in the middle of the program. 2, you can change the values easily. What do I mean by that? They're constants, right? No. What if teachers are going to get paid more, the state increases the sales tax, state tax, something like that. So if you only have to change it one place in your program, you may be using that state tax 100 times in your code. You would have had to go through and change .00623 100 times in your code. But you declare it as a constant. You put it up at the top of the program. You only have to change it once. So you can change the values easily because they're just stored in one place in the code rather than strewn throughout it. That's why you would use named constants. Let you avoid the magic numbers. I will use the term magic number occasionally. There's also magic strings, right? But usually, won't even talk about that. That'd be a named literal. People don't use that term. Magic numbers are the problem. Alrighty. I'm about getting bored of not doing some actual code examples, or at least some pseudocode or something. Let's go see what the next homework assignment might have been. Don't want to do that one. But that'll be a good one to work up to. Alright, what I want to do for the lab portion of our day is we're going to write a little bit of pseudocode for doing more calculations. They're probably not going to even be much more complicated than the last thing that we did. But it's going to set up the homework assignment. Maybe we'll throw in a loop or something. So let's write a program that converts pounds of sugar to calories. I'm going to have to Google that. But let's go ahead and write the pseudocode for it. So I'm going to start my pseudocode off with 3 apostrophes. Those aren't asterisks. I'm going to put a start. I might put some declarations. If I'm going to do it strictly book style, num pounds sugar, LBS underscore sugar, and then the calories constant, num cals per pound. If I ask you to write pseudocode, do you have to make it this wonky, or can you just make it look like the last one we did? The last one that we did is fine. I am showing the book declarations, and I'd be tickled pink if you did it more like this. All right. I haven't defined what the calories per pound is, so I'm going to have to Google that up. How many calories in pound of sugar? Okay, 1775 calories. All right, simplest program would just be one where we didn't even ask any input, right? But that's kind of boring. So why don't we input LBS underscore sugar Now I didn't declare a variable to hold the result. So I'm going to go back up to the declaration section and add one more line. Calories. Calories is a good variable name. So up here in my declaration, num calories. Alrighty, now we need to perform the equation. Calories equals pounds of sugar times cals per pound. I could have just, oh well, you see here, I typed cals per LB there and cals per pound there. I'm going to change that to pounds per LB. Who dictated that LB meant pound? Okay, and then we could output the calories, and then we could stop it. That's our pseudocode. Writing pure pseudocode is kind of boring. So let's write the Python program that'll implement that code. I'm going to be putting comments throughout it that you don't necessarily have to put in your program. My first comment is going to be Python code. My second one is going to be no start and stop lines in Python. It's just reminders. No declarations line, but you can put these things in comments. You can put these things, and like I said, these are just notes. Alrighty. When you declare a variable in Python, you have to assign a value. And the tabs have to follow the rules of Python, not necessarily what the rules of pseudocode are. For example, all of these are tabbed over one more, and we're not going to do that in Python. I feel like changing pseudocode to P code in my typing. I wonder if I could get away with that. The only problem is that P code has a very specific meaning. I'm going to Google that up. P code is a virtual machine designed to execute P code, the assembly language of a hypothetical CPU. Alrighty. Can you remember that P code has a different meaning than what we're going to be using it for, which is for pseudocode? Yeah, you can. Okay, so from now on I might start using the abbreviation P code. Okay. Alright, let's crank it up. I don't mind putting this stuff in comments. Start. Declarations. Now I need to declare my variables. There's no num and there's no set command, and oh, I made a mistake in my pseudocode, but it's the kind that I wouldn't count off for. Remember the word set? I should have put the word set in front of calories. And you leave the word set off when doing Python. Fine. I went back and I added the word set there. I'm trying to write 100% by the book pseudocode. Okay, so our declarations. Pounds sugar equals 0, because you have to assign a value every line, every variable. Cals per pound equals 1775. Now, why did I put that name in caps?
To make it a constant.
Right, because it's supposed to be a constant. And even though that doesn't make it a constant in this language, gentleman's agreement. We know not to change it. Alrighty. Now we need to input. But to input, we have to do three things. We have to prompt, then we have to do the input, and then we probably have to do the conversion. If it's a number, we must. I'm just going to put a comment here. And would I put all these comments in my production code? Input pounds sugar. Not necessarily. You know what? One thing you can do is you can just copy all the pseudocode, put hashtags in front of them, paste it down in here, and then start adding code that solves each little bit, right? But not going to do that. But okay, so let's print a message telling the user what we want. How many pounds of sugar are there? End quote, end parentheses. Then we need to use our input statement. What's the syntax for an input statement? It's not input x, it's x is equal to input. So pounds underscore sugar equals input, parentheses in parentheses. Input is a function. It's a module. That's why it's got parentheses after it. Now we have to convert it to a number that we can do math with. I'm not going to convert it to an int, because what if they type 1.1? We want to support fractional values, so I'm going to convert it into a float. Pounds underscore sugar equals float pounds per sugar. I'm going to put a more generic comment next, which is just convert or calculation. Perform calculation. And that's our equation. There's no set word, so we just do calories is equal to pounds of sugar times our constant. Cals underscore per underscore LB. And now we're going to do some output. Output calories. So print that equals, end quote, comma, and remember I just add spaces to make them more readable. You can skip them. And then the word calories, comma, and then quote. Let's tell them what they're actually saying. Calories, period, end quote, end parentheses. And we're done. So I'm going to put a stop command at the bottom. In a minute, we're going to need to save it and test it. So do file save as. Don't save it into the Python subdirectories. Put it into your own directory. I know I say that, but it's because bitter experience has told me that you can break your Python install. Get it where it doesn't even run. And what am I going to call it? Just June 13. Did I restart the recording? Please tell me. Okay, good. Run module. How many pounds of sugar are there? Well, there are 10 pounds of sugar. That equals 17,000 calories. All right, I'm going to pause it, do walkabout, make sure that we've all got it working. I would like for us to. Doesn't mean you can't upload it as a daily assignment if it's not working. Homework has to work. So I'm going to make a mistake here. I'm going to make a syntax error just to show you how I would fix it. So what I'm going to do is I'm going to run the module. It's going to start working, but then it's going to say cal per lab is not defined. And if you didn't catch what I did, well, here's the line number. I can go look. On my code, it's line number 35. On yours, it would be something else, depending on how you added comments and white space and stuff like that. So I need to find line 35. Well, great, it's not even showing me the line numbers. Well, maximize the code, and you'll see line numbers down here in the very bottom. It'll show that your cursor is currently on line, 29, 40, something like that. And then you just move your cursor up and down until you find a line number that matches it. So what line am I on? I'm on that one, right? And then I look at it. What did the error message say? The error message said something to the effect of that variable is not defined, right? Cal per lab is not defined. And you throw a fit and you say, oh, I defined it. Compare it. Usually that's just a typo. Cal per pound, and it'll go, oh, yes. And so you go and fix that. Other common syntax errors, leaving off commas and things like that, right? So if I did that and then I ran it, it would start running. Nope, this time it didn't even. Okay, this was kind enough to actually highlight the problem, but not really, right? What does it look like the problem is?
The quotation.
It looks like the quote's the problem, and is that the problem? No. So if what it highlights is not the problem, kind of scan your eyes backwards and see if you spot it. And in this case, it's because everything has to be separated by commas. Sometimes you even have to go to the line above. Like if you do this, print, parentheses, hello, but you don't close the parentheses, it's not going to consider that line a syntax error. Or yeah, it probably will. But I'm trying to give an example of when you have to look on the line above it. Yeah, there we go. This will drive you crazy. That's not a syntax error. That's a perfectly good word. The problem is on the line above it. Every print has to have a closed parentheses. So it does a good job of showing you what it thinks the error is, but it sometimes won't show you what the reason for the error is. And the reason is that there was a missing parentheses above it. That's just what makes programming fun. All languages are like that, not just Python. They can't show you exactly what you did wrong. All they can show you is the point where the compilation stopped working. Why did the compilation stop working there? Because it was expecting a closed parentheses before it got to that point. Everybody get it going. Anybody need more typing time? All right. Since this doesn't have any if statements or anything like that in it, that would be a pretty boring one to flowchart. Ought to make us do it anyways, but like I said, it's not really a very interesting flowchart. I think we're going to do it anyways, though. But what do we flowchart from? It's easier to flowchart from pseudocode. And why do I say that? Because even if I removed all these comments, I'm going to copy and paste this code without the comments. Just because. You have to do that? No. I'm going to remove the comments. Why am I doing this? Because you could get that code and then have to flowchart it. And you could. You go, okay, I'm going to need a start, and I'm going to need a stop, and these look like declarations, and I know what print statements go in. But all three of these things were just one block, right? That's the input block. You could go ahead and put all three blocks in your flowchart, but that's going to take 3 times as long. If you were doing this on an exam, you wouldn't want to take 3 times as long. If I'm going to ask you to draw a flowchart, I will probably give you the pseudocode. Another reason I showed you this is that comments are great, but sometimes they add visual noise. What do I mean by that? This code is easier to read if you don't know what the code is doing. But maybe you don't need all those comments. You might just put a comment up at the top. Input pounds, calculate, and display calories. Right? That would be enough. And then when you were scrolling up and down, you would know that all of this code applies to that. Maybe it's easier to read, maybe not. You just have to pick. People tend to write more like this than they tend to write like this. But breaking up your code into paragraphs is a good thing. Makes it easier to read. If I was going to write this code, I at least would have done a break right here, because that's the calculation line, and I would have put a break right there. Oh, why do I have that word hello anymore? Need to delete that word hello. Okay. Just to make it easier to read. That's your goal. One of your goals is to get the program working. The other goal is to make your program easy to read. And one rule of thumb is people sometimes try to make the most efficient code possible. And a rule of thumb is write first, optimize later. Why is that? Because computers run so fast and have so much memory available to them that optimization is not nearly as important as it was in the 70s when you had, computers that had only 64K and they ran, not in, they ran in hertz rather than gigahertz like computers do now. And that sounds lazy, but it's not. You could spend days, weeks optimizing a program that was already fast enough. Now, if you're writing a game and you're writing video routines and stuff like that, yeah, you are going to try to make the most. But just get it working first and then start speeding it up if it's not fast enough. Python's not the fastest language. We're really not going to optimize. Flowcharting time. I put that down there. I'm going to delete it now because we already have this code up here. And as a matter of fact, I'm going to base my flowchart based on this pseudocode. And somebody asked me a very good question, which is, how do I upload both the pseudocode and the flowchart? There's 2 ways. You could paste the code directly on the flowchart, but all I'm expecting you to do is to upload 2 files. You can upload multiple files into D2L. Now, when I was getting my last degree, I took classes from a teacher who only allowed you to submit 1 document to D2L, and that was your final answer. You couldn't replace it with an, nah, wait, don't allow that. Okay, so I'm going to go into Lucidchart. If you remember, it's lucidchart.com, or you just type Lucidchart and go to the first hit in Google, whatever. Log in, but sign in with Google. Use your email address. And hey, if you feel like using Visio, the Microsoft version of flowcharting, totally cool. And then what am I going to do? I'm going to make a blank document. I don't know why it offers also to make a flowchart. Blank document, perfectly good way of getting into it. All right. Now, I feel like having my pseudocode on the same document. Do you have to do that? No, but I really would like for you to put your name on these things, right? And then I'm going to hit Control Enter and put what the program is. Calories calculator. That's enough, right? I'm just going to shunt that off to the side. But I'm also going to put the source code. Well, not the source code, but the pseudocode. How am I going to do that? Same way. The only problem is it's probably going to remove all of our tabs and stuff like that, which is kind of a drag. So I may delete it. I may not take the time to fix the tabs when I'm done. But for now, I'm going to grab my pseudocode. I'm going to copy it all. Control C for copy. I'm going to click on here and I'm going to hit Control V for paste. And that's kind of lame. It looks like it kept the tabs, but what's wrong? It's not. It's centered. It's not left justified. So you can right click on your text and do.
You're gonna have to highlight the words by the looks of it.
Yeah, you're right. I need to double click on it to highlight all the text. My mistake. Thank you. Right click. Still not there, but hopefully I can come up here to alignment. So I'm going to double click in the middle of it to highlight it. Oh, come on. It's not letting me do that now. Okay, fine. Click, drag, get the whole thing, come up here to the centering tool, the alignment tool, and say that you really want it left justified. That's better. And it's got all these spaces in here. I'm going to remove all the spaces. Yay. Okay. Do you have to do that? I don't require you to put your pseudocode in there. Why do I want that right now? Because otherwise I have to keep flipping between the documents and my screen space is limited. It's the only reason I did that, really. It's kind of cool, though. Okay, so here we go. What do all of our flowcharts begin with?
Terminator.
Yep. I think I read that they're making a new Terminator movie where the same Terminator is both the good guy and the bad guy, and I don't think that's been done before. But it's a perfectly reasonable idea, right? Because they're machines, you could have hundreds of them. Okay, I'm behind in my Terminators. I don't know if that's the case. Start. Okay. Maybe that's been a plot point forever. Okay, so start, and then I have my declarations. Declarations, whether single or multiples, just go in a box.
So you can put two declarations in a box. So you can put pound of sugar equals 0 and then cows per pound 17.
Exactly. Especially, I mean, if it's a if you're doing a whole bunch of math formulas, don't put them all in one box. Right? Like if you're going to calculate the surface area, and then you're going to calculate the amount of paint that it takes to do that surface area, and then you're going to calculate the price of the paint. Don't just throw all, don't copy and paste that. But declarations, yeah, totally okay to put them all in one box. I think the book even shows putting the word declarations in them. You don't have to do that. But okay, declarations, Control Enter, and I'm going to declare my variables. Num pounds underscore sugar. Control Enter. Nums cows per pound equals 1775. If I feel like it, I could widen the box so that it looks a little bit better. If I really felt like it, I could write justify all the text, right? Not sure I like that. I'm going to center it. And then I draw a line to hook the things up. Alrighty, what's an input go in?
Diamond? Yeah.
Not that looks like a diamond, but the tilted rectangle.
The quadrilateral, more specifically the data block.
Yeah.
Yeah. So I'm just going to grab a data block, pull it over here, and I'm going to do input LBS underscore sugar. All right, what's the next line? It's our calculation.
So set calories equals pounds sugar.
Remember that all this stuff is a little bit loosey-goosey. I wouldn't mind leaving the word set off.
Would the print line have to be in there too? The print, how many pounds of sugar are there?
It could totally be there.
But it doesn't
But since
have
we're
to.
taking just P code and turning it into a flowchart, you don't have to. And the reason for that is that the syntax for this stuff varies. Maybe we're just reading this stuff from a file rather than asking the user, stuff like that. We're leaving it kind of generic. Yeah, if I'm giving you pseudocode and I'm wanting you to turn it into a program, it's very possible that I'm going to put the print statement and the conversion statement and stuff like that, but it's not necessary. You make these as detailed as you think would be useful. Okay, so our process block. Set calories. I told you I'm going to leave the word set out. Calories is equal to pounds underscore sugar times caps cals underscore per pound. You feel like widening that? Totally cool. Well, that was wide. That's enough. Here's a trick. In a great many drawing programs, if you grab a side and restretch it, it only stretches that side. But what if you want to stretch it and keep it in the same position? If you hold the Alt key down, the Option key down while stretching it, you see what it's doing different?
Oh, wow.
Thank you.
You're totally welcome. That works in a lot of drawing programs. Okay.
Moving my arrows.
And moving stuff around, yeah. You can use the cursor keys, but you still get annoyed with it.
So how'd you just do that and go?
I grabbed the mouse and then I used the cursor keys like that.
So you just click on it and you just use
You just click on it and use the keys and you can move the stuff around.
I was just utilizing the mouse itself in one sit.
Which is fine, yeah.
If I can never get it back, I can never get it to go straight again.
Right, once you move it, it becomes a problem to get it straight. And then sometimes it gets to the point where you can't really select that arrow. See, I'm trying to fix the arrow and I select that. Here's what you ought to do if you're trying to make fine adjustments. And if you don't feel like taking the time, I'm not going to count you off for the art of it. Hold the Alt key and zoom in. Alt key, spin the mouse wheel, zoom in. Then you can grab the arrow and you can make fine adjustments too if you care.
I lost count of how many times I deleted it.
Mm-hmm. I'll show you one more trick at the very end of this, where sometimes I leave drawing off all the arrows until the very end and I draw just one big arrow, and kind of cheat. I'll show you what I mean. Alrighty, we've done the calculation. We need to output the calories. People have made efforts at creating visual programming languages where you program by dragging blocks, you know. Kind of a cool idea, but you couldn't write great big huge production code like that. As learning tools, they're okay. Yeah, now I've resized it and I messed up the arrow. So I'm going to resize it holding the Alt key. It still messed it up. Alright, fine. What am I going to do? I'm going to zoom way in. Click on the arrow, fix it. Do I care if all the arrows line up exactly? Nah. And then lastly, we were done, so I'm going to add one more terminator. All right, there's my flowchart. I'm happy enough with that. I think this.
Upload that into the assignments.
Yeah, so we're going to do a file, save as, and then a file download as PDF. And I apologize for not getting back to you, but I'm glad you figured it out. You sent me a text saying, "How do I get that in there?" While we're talking about, just common Windows, shouldn't call them tricks. If I could not find a way to download this thing at all, it'd be okay just to take a screenshot. How do you take a screenshot? I may have mentioned this, but you just hit the print screen button above the numeric keypad and then open Word or a Paint program and paste it in there. Then you could upload that. That'd be totally cool. All right, so file, save as, June 13, calories. And then file, download as. I like PDFs. If you were going to paste it into a Word document, you'd download it as a PNG instead. And if you pasted your Python code into the flowchart, you don't have to upload the PY script, but what's wrong with uploading the PY script? Go ahead and give me the PDF and the PY. Let's make a Dropbox for it. All right, so the homework is going to be writing a program, specifically the pseudocode and the flowchart, but I'd kind of like you to do the program as well. Usually I make them separate assignments, but the class is moving twice as fast. So, what is the task? Task, calculate BMI, which is body mass index. And the idea behind BMI is you take your weight and you run it through some kind of conversion. You divide by your height in inches and it pops up a number. And, and then some doctor or insurance table will go, well, this is overweight or this is underweight, that kind of stuff. And BMI is not really a good indicator of health because a football player will always show up as being overweight just because they're big and have lots of muscles, whatever. And, some people are naturally thin. Doesn't matter. But it makes it for a good program to write. So our task is to calculate BMI. The formula is BMI is equal to, and that's just our formula. So what are we going to do? Ask the user for pounds. We're going to ask the user for inches. We're going to calculate the BMI. Now I've already pretty much written the whole program. I mean, not the whole program, but the whole pseudocode. So I'm got to change this a little bit. Calculate and display the BMI. So I'm going to call this one part 1. I would like y'all to go ahead and take a good stab at part 2. Write the Python code that accomplishes the task. All right. Some people have taught the course using entirely pseudocode, never using a programming language. I think it's far more fun to learn a programming language at the same time. All righty. I think we're done for today.
I had a question about the hexabinary.
Oh, yeah, sure. Let me pause this and see if it's a question I need to cover for everybody. Okay, so hexadecimal to decimal, 16 to base 10. The way you set it up, say I want to do A1, A5, A6. Okay, to decimal. What you got to do is you got to remember your powers of 16, and if I've given them to you on the worksheet, you don't have to remember them. But they are 1, 16, 256, and what is the other one?
4096.
4096, okay. And then you set the numbers up underneath them. There's an A, there's a 1, there's an A, and there's a 5. Okay, so then we're going to add them all up. And I'm going to type in just the letters and stuff like that, but then I'm going to go and replace them with the real values. A times 4096 plus 1 times 256 plus A times 16 plus 1 times 5. But what is an A, really? Hexadecimal works like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And decimal goes the same way. But what is that? That's just a 10. Come on, type. A 10, an 11, a 12, a 13, and a 14, and a 15. Like that. Okay, so I'm going to replace these A's with their decimal equivalent. What is an A?
10.
A 10. I didn't throw in anything else other than an A, so okay. And then that's enough. That is the answer. Yeah, you could whip out a calculator and do all that math, you know, to get the answer, but that's what the worksheet's wanting you to do.
Gotcha.
Okay.
Yeah, that was just a small question I had.
Yeah, that is a very good question, and this is kind of alien stuff. So, you know, I know that in the new math or things like that, people actually did base conversions in elementary school or junior high and stuff like that, but I think it's new to almost everybody. Any other questions? All right. Have a good weekend. If you get stuck on something, text me. Read chapter 1. Take the test because we're well done with chapter 1. I know that a lot of people actually hadn't gotten their books. Now you're in it, so hopefully you can do it. For those of y'all who had to follow the alternate link, you're not going to be able to get into the chapter 1 exam by using our contents menu. Right, you're just going to open the book, open the Mind tab, and then find Unit 1, Chapter 1, and then find a test that way. And I apologize for it not being easier than that. If you get stuck, text me and I'll show you.